Hello, welcome to our second unit where we're talking about derivatives in depth. This will be a really good chunk of the course. We talked about the limit definition of the derivative last time, and this tells us that the derivative gives you the instantaneous rate of change of a function at any particular point you like. So the derivative of a function is itself a new function which tells you instantaneous rate of change. Well, now we're going to talk about techniques for finding derivatives, which will end up being a lot easier than taking a limit. And that's especially true today. All right, so this is called techniques for finding derivatives. You could essentially call this this little lesson power rule as well, but I'm sticking with the book. So here's power rule. It's a rule for calculating derivatives, essentially of polynomials. The derivative with respect to x, just meaning x is our variable. The derivative with respect to x of x to the n is you bring the exponent down times x, now to the n minus 1. So you subtract 1 from the power, and you're multiplying by the old power. And this is where n is a real number. For example, if I take the derivative of x cubed, we don't need to calculate a full-on limit. We just use the power rule. You bring the 3 down times x, and now we subtract 1 from the old exponent. So 3x squared. As we get further into the course, this should become second nature to you. Here's some good news. Derivatives distribute over addition and subtraction. Derivatives play really nicely with these things. This means that the power rule works very well for polynomials. You just apply that power rule to every term. I've come to edit from the future with a quick rule of thumb involving derivatives. So what happens if we have a constant out front of any function? So I have this times k, think of it like a times 2, or something like that. Then in this case, we have this nice derivative rule, which tells us we can basically ignore the k, move it off to the side, and then get to taking the derivative of our function, f of x. So for example, applying this to power rule, if I'm taking the derivative of 4x cubed, then I can move the 4 out, essentially ignoring it, and then just get to taking the derivative of x cubed. So bring the 3 down, times x squared, subtracting 1 off that power. So because I have a times 4 out front, it just comes along for the ride. Here, I'm just going to use the alternate notation. Remember, there are a couple ways to write derivatives. If f of x is x to the fifth minus 4x squared plus x, then the derivative, f prime of x, normally I won't show this much work, but since we're just getting started, we're taking the derivative of every individual term. Plus the derivative of x. So the derivative of the entire polynomial is found by taking the derivative of each individual term. You're allowed to do that when you have addition or subtraction. Now, is that the case when it comes to multiplication? Not so much. We'll get to that in the coming lessons. Let's finish this. Derivative of x to the fifth. You bring the 5 down times x to the 4, taking 1 away from the 5. Maybe I'll show a little more work here. We're multiplying the coefficient of 4 by 2 because that 2 is the old power. Times x to the first, or just x. Well, x is x to the first again. So think of it as a times 1. It's the old power. X to the 0 is just 1. So the derivative of x is just 1. Let's finish this. There we go. So again, the derivative of the entire polynomial, f of x, was found by taking the derivative of each individual term. You're allowed to do this with subtraction and addition. Now, another derivative fact, which really follows from power rule, but I just want to highlight it. If you take the derivative of a constant, so when I write d dx like this, I'm saying x is my variable. Notice there is no x in here. K is a constant, a fixed number. And if that's the case, then the derivative is 0. Let's say if k is constant, so I'm saying k is just a number like 2. You take the derivative of 2, you get 0. Another way to think about it is that the derivative measures rate of change, instantaneous rate of change. And if the function is constant, like k, then there is no change. Hence, the rate of change is 0 everywhere. But let's work this out from power rule. This really is just an outworking of power rule. This is because k you can think of as k times x to the 0. X to the 0 is just 1. And then if you apply power rule to this, so I'm taking the derivative with respect to x, we're multiplying by 0. Okay, technically 0 minus 1. But doesn't matter too much because we're multiplying the whole thing by 0. So the derivative is 0. Let's take a quick derivative involving a constant. So I probably won't show this much work in the future, but we take the derivative separately of each term. The derivative of 2x is just 2. You start to see that whenever you have these linear derivatives, x to the first, you just pick out the coefficient. It's like the slope of the line, essentially. Plus 0, because 0 is the derivative of the constant 1. Now this gets a little trickier. And again, I want to switch over to the f prime language just so we experience both that and the ddx. Now this may look a little different, but turns out power rule does apply, because as we mentioned in our lesson on exponentials, these radicals can be rewritten. I think that was in the same lesson. Anyway, that was probably rational exponents. Let's write it this way. The derivative of x to the 1/2, because x to the 1/2 is the square root of x. Same thing. I could write the 12 in there or write it as a sum of two separate derivatives. Same thing in the end. This 12 does essentially nothing when it comes to the derivative because it's unchanged. So its derivative is 0. So this rational exponent notation for the square root is useful because power rule works on it. So bring the 1/2 down times x to the 1/2 minus 1 power, and then plus 0 for the 12 part. So we have 1/2 x to the minus 1/2 well, that negative exponent means that x to the positive 1/2 lives in the denominator. And now we can, to finish this problem off, we can write it again as a square root. Notice that this is the same derivative we calculated last time when we were taking the definition of the derivative to find the derivative of just the square root of x. We didn't have the plus 12 there that time, but it doesn't make a difference here. Same derivative. right. Let's use some different letters because we can, and you'll see this on occasion. G of u, g being the function, u is the variable, u to the 0.9 minus u to the 1/5. Notice this is the same thing as the fifth root of u. And if we want to find the derivative of g with respect to u, we just apply power rule to these terms. 0.9 comes down, u to the 0.9 minus 1, minus 1/5, u to the 1/5 minus 1. So that is 0.9 u to the minus 0.1 minus 1/5 u to the negative 4/5. We could change the form of that if we want to, but doesn't seem necessary to me because it's a similar form to how we started the problem. And so even though these things look nasty, power rule just applies, and it's not too bad to perform. Now here's something a little new. Say f of x is 1 over x plus the cube root of x. And if we want to take the derivative, we want to rewrite both of these so that we can use power rule. Namely, think of 1 over x as x to the minus 1 power. And I'm just thinking of these as two separate derivatives, plus the derivative of x to the 1/3. That's the cube root of x. And now we're set up to do power rule. So the negative 1 comes down, x to the negative 1 minus 1, plus 1/3 comes down, times x to the 1/3 minus 1. Now this simplifies to negative x to the minus 2 plus 1/3 x to the negative 2/3. And now I'll just clean these up a little bit. So that negative 2 exponent means that I can write it as an x to the positive 2 down in the denominator. Okay. And we have a negative exponent here as well, so that can be a positive exponent if it's moved down to the denominator. Now x to the 2/3 down here, I'm going to choose to rewrite a couple ways we could do this, but I'll write it as the cube root of x squared. That's one way you could write that. So zoom out a little bit so we can see the original. Yeah, so you can think of the derivative of 1 over x as this part, negative 1 over x squared. And this is the derivative of cube root of x. Okay, next. Let's do an example where f of x is a fraction x cubed plus x to the fifth all over x to the fifth. And we want to find the derivative of f. Now, it looks difficult to apply power rule at first, but this is actually very doable if we just split up this fraction in two. F of x can be rewritten as x cubed over x to the fifth plus x to the fifth over x to the fifth. So sum of two fractions with that same common denominator. So I haven't done any fancy derivative rules yet. I'm just rewriting the original function. And now we are poised to be able to take the derivative. If we simplify a little bit, 1 over x squared by canceling. And the 1 over x squared, to set it up for power rule, it's easier to write it as x to the negative 2. So then f prime of x, negative 2 comes down times x to the negative 2 minus 1. And then plus 0 because derivative of 1 is 0. 1's a constant. So we get negative 2 times x to the minus 3, or negative 2 over x cubed. Now, the last problem I want to do in this lesson is related to tangent lines. We want to find all values of x where the tangent line is horizontal. And here's my f of x. 1/4 x to the fourth minus 1/3 x cubed minus 21 x squared plus 10. So this is my function, this polynomial. And we want to find all x values where tangent lines at those points will be horizontal. Now, this ends up being not as difficult as it sounds once you make the connection between tangent lines and the derivative. That's the key. So remember that the slope of the tangent line at some x value, it's a different tangent line at any x value. So the slope of the tangent line at an x value is the same thing as the derivative evaluated at that point. These are the exact same thing. So if we're talking about finding a horizontal tangent line, what does horizontal tell you about the slope of that tangent line? It's 0. Slope 0 means your line is horizontal. This means we want to find where the derivative is 0. Because horizontal tangent line means the slope of the tangent line is 0. Which means that the derivative is 0. Because the derivative is the same thing as the slope of the tangent line. So no need to make a fancy graph or anything. We don't need to know what the graph looks like at all, actually. We just need to deal with the derivative. So we're essentially asking, when is the derivative equal to 0? And pretty good rule of thumb that, at least for a good while in this course, if you have a word problem and you're given a function like this, most likely you're going to be taking the derivative of that. I won't promise that's happening all the time, but that tends to be a pretty good rule of thumb. Need to zoom out a little bit so we can see that f of x there. So we get 4 times 1/4 times x cubed. That works out pretty nice. Bring the 3 down, times 1/3. Now it's x squared. Subtracting 1 from this old 3 exponent up here. Minus 2 times 21. Just x now instead of x squared. And that plus 10 does nothing at all for this problem. I could have written plus 2 minus 1 plus pi. It wouldn't have made a difference because derivative of a constant is always 0. So we've got it. Simplify. We get x cubed minus x squared minus 42x. Now our goal is to set this equal to 0. Because we're trying to find the x where this derivative is 0. So we're solving a polynomial. Now we don't have a lot of experience with solving cubic polynomials like this, where you've got the x cubed. But this quickly turns into a quadratic problem when we factor out an x. I set this one up so that we have an x in every term. I think I want to use arrows. So we factor an x out of every term. And now this becomes doable. Now this might seem like a difficult one to factor, but it is doable without quadratic formula. Once you recognize that 6 times 7 is 42. And 6 and 7 are 1 apart. That's how we can get this guy. So if we have plus 6 and minus 7, these numbers multiply to give us negative 42. And they add together to get us negative x. Or the negative 1 coefficient in particular. And now we're basically done. Since we have this product of things equal to 0, that means that the pieces themselves must be 0. Those are the only solutions. So either x is 0, or -6, or 7. It's at these points where we have horizontal tangent lines because the derivative is 0 at these points. That does it for this lesson. See you next time when we get to product rule.